Alright everyone, let's take a look at section 21B, which is called derivatives at x is equal to a. Now this section here, really what we're going to be doing is more or less just practicing how to determine the instantaneous rate of change for a function at a particular value on the graph. So remember that what we said yesterday is that the instantaneous rate of change at a particular value x is equal to a is actually going to be equal to the limit as x approaches that value of a of the average rate of change. Now what we said, of course, was that the average rate of change was going to be calculated by the slope. So we can then go ahead and say that this is going to be f of x minus f of a divided by x minus a, being that the two coordinates that we had were a and f of a and x and f of x. Then what we said then is that another way of actually representing very simply the instantaneous rate of change at x is equal to a is we can just say that that is f prime of a, and that is the derivative of the function f of x at x equals a. So let's go ahead and just look at what we did the previous lesson, and let's go through the process again just to make sure that we're okay to determine f prime of 2 if we know that f of x is equal to x squared. So if I go ahead and substitute in the value of 2 for a, I substitute the value of 2 in for a, substitute the value of 2 in for a, and I also know that f of x was equal to x squared, and x of course is just x. So what we know then is that the limit as x approaches 2 of x squared minus 4 over x minus 2, if we were to go ahead and substitute, let's stop right here. If we were to go ahead and substitute the value of 2 in for x, notice that what I would come out with is 4 minus 4 divided by 2 minus 2, which is 0 over 0, which we said had no meaning. So what we're going to have to do then is we're going to try to algebraically manipulate this, and what we should notice is that we can factor. So I can factor it this way, and now I can cancel out the x minus 2 factors to come out with just x plus 2. Now I can go ahead and say what happens when x actually gets closer to 2, and in other words substituting the value of x equal to 2, I come up with 2 plus 2, of course, which is 4. So what happens then is I can say then that the instantaneous rate of change at x equals 2 for this function f of x is equal to x squared, the instantaneous rate of change, or the slope of the tangency line at the point 2, 4 is going to be 4. And that's what we did yesterday. And what we're going to be doing today is more or less continuing to practice this. Now, of course, one of the things that you're going to see is that we want to be able to determine what the instantaneous rate of change is based upon this definition here of the instantaneous rate of change at x is equal to a. If you use this, you call this using first principles, because you're using the definition of what we call instantaneous rate of change at x is equal to a. Now, in addition to using this formula, which is based upon first principles, there is a second formula that is also possible to use to calculate the instantaneous rate of change at x is equal to a, and it's based upon the same concept here, except for the fact that it looks slightly different. Okay? Now, we'll talk a little bit more about why this is true, but let's just go ahead and take a look at how to actually use this. Now, if we have f prime of a is equal to the limit, notice that we have this value h now. As h approaches 0, we have f of a plus h minus f of a divided by h. Okay? So this is going to be another valid means of calculating the instantaneous rate of change, just like this here. Okay, so let's go ahead and do the same thing, and let's determine what is f prime of 2 for f of x equals x squared, but using this formula here. If we were to go ahead and substitute the value of 2 in for a, then everywhere here where there's an a, of course I have to substitute in a 2, and notice that's the only value that we have to substitute in. So once I go ahead and I square this, because that's what f of a plus f of 2 plus h is the same thing as 2 plus h quantity squared, and of course the a is 2, then 2 plus h quantity squared is 4 plus 4h plus h squared, and the f of 2 is 4. Now notice, if I was to go ahead and just substitute in that h is equal to 0 here, of course the denominator is 0, this would be 0, this would be 0, 4 minus 4 is 0, so we'd still come up with 0 over 0, which is not a possibility again in mathematics. So what we need to do is we need to simplify further, and let's go ahead and notice that we can cancel out the 4's, and what we're left with is 4h plus h squared divided by h. Now notice I can factor out an h, which would mean then that I can cancel that out. In other words, I can rewrite this line here as the limit as h approaches 0 of h times by 4 plus h, all divided by h. Notice that the h's then can cancel. And that's why I can come out now with the limit as h approaches 0, 4 plus h. Now if we go ahead and substitute the value of h, now if we substitute the value of 0 in for h, because we're taking the limit as h approaches 0, notice that what I come up with is 4, which is consistent with what we have here as well. So notice that using either this formula or this formula here, we can always go ahead and calculate the instantaneous rate of change at x is equal to a for a given function f of x. Okay, so there's consistency there, and the book will determine which formula you should use to be able to go ahead and evaluate the f prime of a. Okay, well, let's go ahead and see if we can work with that tomorrow or the next class and make sure that we can use both of those formulas to be able to calculate f prime of a. Alright, see you later. Bye-bye. Rate of change.